will just give a very short introduction for Kjeld Beeks. So he was born in the Netherlands and studied at TU Delft. And then he joined the group of Thorsten Schum at TU Wien. And this is where he started some of the work I think that we will present today on exploring some nuclear transition in the deep UV, I don't know what it's called, this wavelengths, which could be used eventually to build nuclear clocks and other applications in quantum optics, as he will probably detail today. So basically, the first paper apparently of a series, which is now coming out, came out a few weeks ago or months ago or so. So I exchanged a bit with Thorsten to congratulate and then okay, my former student is here at EPFL, so I didn't know. And I thought it would be a great opportunity to have him present these results here to our community. So please, go ahead.
Thank you very much. Thank you very much. Welcome everyone. Kjeld Beeks, of course. First in the group of Thorsten Schum, now in the group of Fabrizio Carbona. And today I want to talk about nuclear clocks, sort of the first step quantum device 0.0, basically that one could do with nuclear excitations, and a bit about nuclear quantum optics. But this is more of a further future where I'm like really trying to extend it not from the deep UV, as Christoph said, but really into the X-ray regime, basically, even higher energies. If we could actually make sort of coherent beams, coherent pulses, that would be good enough to do some of the quantum engineering things that you guys possibly are doing. And obviously, since we're talking about nuclei, we always talk about isotopes. So in this case, in a way, like from thorium-229 in crystals to electrons surrounding gold, 197. So to bridge a little bit of the gap between sort of the electronic and the nuclear, I want to talk a little bit about like, what we would call quantum oscillators, where also clocks are based on. And I'm referring to clocks because we're trying to build a clock, but also because they were kind of the first devices where we could really use the quantum properties to discover new physics. So the very simplest system that was used before, the microwave clocks, where you actually flip the spin of the electron that is obviously coupled to the spin of the nucleus, and the energies that are involved in sort of this spin flip is in the microwave regime. So these were like the first clocks, the first Rabi oscillations, the first Ramsey interferometry, etc. The energies are like gigahertz or micro electron volts. And very often we like to talk about the Q factor or quality factor of the oscillator. Basically tells you how much damped the oscillator is. And these excitations are quite robust, and usually they put them in a gas cell. So you can just have a gas cell, and they do spectroscopy by shooting microwaves at it and kind of looking at what comes out. And obviously one of the first applications there was the rubidium-87 clock that is now on many GPS satellites and the likes. Quite small, like a box like this, basically, where they probe this microwave transition in rubidium. And just to remind you, this Q factor is basically the frequency or energy of the resonance that we are talking about, so in this case the spin flip, divided by its line. Because in that sense, it just the fundamental harmonic oscillator, this tells you how damped the oscillation is, says a bit about coherence time, etc. Very often people use for these kind of like clocks, or when they want to have a long-lived new excited state, forbidden transitions. I mean, maybe I'm using this term a little bit broad, but in that sense it should be a long-lived state, and usually it's because it is not allowed to decay to any other state in a reasonable amount of time. Very often that means it's like a magnetic monopole, an electric quadrupole, or just that the quantum numbers do not follow the selection rules. And just to remind you, the selection rules are basically just sort of an overlap of the wave functions of the different states. By the way, if there's any questions at any point, stop me, basically, because I will maybe sometimes go a bit quick over things because there's much to tell, but in every slide there's a whole story to tell. So what we can do and what has been done in history is increase the Q factor. Like how can we get better clocks, better oscillators, better coherence time? I mean, I know that some of you guys might work with NV centers, quantum dots, etc., which is obviously a little less like a fundamental oscillator, but more like a more complicated system already, but let's keep it simple. So if you increase the Q factor, you would get to like an atom. And then usually you would probe an electronic transition, so an excitation of electron from one orbit to the other one. Usually we probe that with lasers, and the frequencies of that is in the hundreds of terahertz range, or in the electron volt range, or what is it, 1,000 to like 300 nanometers or so. The Q factor, as you can see, increases by several orders of magnitude. But very often, at least in atoms, these states are relatively fragile. So you'll see that these things are trapped in like a optical lattice, basically, or they're trapped in an ion trap or things like that, basically, in order to make sure there's no external perturbations while I'm probing this quantum state. And a good example is the recent success with the strontium-87 clock, where they made the most precise clock to date. And if you know a little bit about clocks, you know that the cesium clock is the standard. That's still sort of based on a microwave transition, basically. But at some point in the future, I think in like 5 years or so, they want to change the standard, the definition of the second, towards the optical clocks, basically. And which one is still a bit of a debate. So now comes sort of the nuclear step. If I want to increase the Q factor even more, I want to go further than we've gone before. I of course want to go to a nucleus, but how does that look like? Well, the thing is, at the moment, the only way we have to excite nuclei are, in principle, free electron lasers or synchrotrons. They are the only sources that can produce X-rays at high enough intensity. I'm now not talking about radioactive decay, like that's something nature has given us, with which we can also excite nuclei, with, for example, Nussbauer spectroscopy. But it's a process we cannot control. It happens, but we can't change it or anything. The Q factor will be even much higher, and the nice thing is that because the frequency domain is so different from the world around us, they are quite robust against external perturbations. They're also really small, so for example, any gradient in the electric field or magnetic field, they don't feel so much. So you can just put it in a solid, you can have a metal, basically, just a piece of steel actually, and you can probe a very narrow nuclear excitation in that already. And a very nice recent result on that, I'll talk about it later a little bit more, is they managed to probe the scandium-45 clock transition, they call it, at 14 kilo electron volts X-ray. And the clock part about it is that the narrowness of the transition is only femto electron volts. So if you then look at the Q factor, right? So we have the frequency, or energy, is 14 kilo electron volts, over the narrowness of the transition, which is femto electron volts. You get a very, very high Q factor. It could make an even better clock. But also, you could also have a qubit, for example, with a very long coherence time, or storage time. So you can think about qubits and stuff. Well now, we were talking about this deep UV, nuclear excitation, and how does that one fit in? So basically we took kind of a side step from this like ever-increasing Q factor, where if we take the thorium-229 nucleus, which is a very special nucleus, because it has a very low-lying first nuclear excited state, at, to have the exact number, 148 nanometers. No, not super exactly. 148 nanometers. Only 10 electron volts, and this is something we can still probe with lasers. We can use almost exactly the same techniques as that people use on atoms in order to probe this nucleus, or at least it should be possible, and like Christoph said, we've actually shown that it's possible. So the Q factor is just a little bit higher than for the atoms, basically. It's robust, and we can produce it as doped in a solid. The only thing is obviously, like, just probing this is not enough, right? If you know anything about optical clocks, they do very sophisticated things to make sure that there's no external perturbations, to measure the magnetic field, they do all kinds of quantum operations to really make sure you can probe the natural line width as good as possible, to have a very long coherence time on the order of 100 seconds for strontium actually. And all that development has not been done for nuclear yet, basically, but that could come in the future. And here's a little image of one of the crystals I produced in my PhD. It's a very tiny crystal, it's about this big, basically. And the blue light that you see through it is the EUV or the VUV laser that actually goes through the crystal and produces some fluorescence in the visible. So this is not fluorescence from the nucleus, this is invisible. So this is the first part I will talk about, the nuclear clock, and then in the second part I will go a little bit more into how can we extend this into sort of a nuclear range. So because I was talking about forbidden transitions, usually in an atom it's just forbidden and not many other processes happen. But in the case of a nucleus, because the energies involved are also higher, I want to talk just a moment about different nuclear excitation processes and de-excitation processes. So if we have my atom, basically there's two processes I want to highlight, called NEAK and NEAT. NEAK is an abbreviation for nuclear excitation by electron capture. So the nucleus captures an electron and gets excited. NEAT, very similar, nuclear excitation by electron transition, meaning that an electron which is bound goes from one excited state to the other and the energy matches the nucleus. So in a more pictorial way, let's imagine an electron that flies by an ion, because then they can capture the electron obviously a bit more easy, which has a certain kinetic energy. Then it can be captured by the ion. It obviously, some binding energy will be gained. And in the end, if that kinetic energy and binding energy is resonant with the nuclear structure, so with the nuclear excited levels, you can excite a nucleus. And the thing is that this process is often more efficient, or the cross-section of the excitation is much larger than direct photoexcitation. Because obviously direct photoexcitation is always possible, but because the multipolarity is different, or because the quantum numbers don't match, these kind of processes often have a much larger cross-section. And that's why I also put like angular momentum in there, because the thing is what you need to match is obviously angular momentum of the orbits, but also the nuclear structure, right? I haven't talked about nuclear structure. If somebody wants some explanation about nuclear structure, just to give like one thing, the nucleons, when you actually calculate the nuclear structure, are not point particles. They do not behave like point particles. It means if I want to calculate the excited states of this ensemble of protons and neutrons, I need to take into account many, many different factors in the Hamiltonian in order to actually make an accurate theoretical description of the structure. And so the quantum numbers, as we know them from electrons, are actually not as well defined, or do not apply so well to nuclei. They also have irregular shapes. There's pear-shaped nuclei, elliptical nuclei, etc.
Sorry, this electron is being captured by the nucleus, and it's not a part of the atomic. Right?
No, it's captured in the atomic orbital in this case. It's because if it would be captured in the nucleus, it would obviously change to another isotope, right? This would be transmutation. That's possible as well, but the energy scales are very different. Because transmutation would happen at like 10 to 20 mega electron volts, whereas these nuclear excited states are more in the tens to kilo electron volts to 1 mega electron volts. So basically, to really get into the nucleus, you need other energy scales. But there is some communication, obviously, between the atomic orbitals and the nucleus. So there's like, for example, the 1s electron spends some time in the nucleus, basically, like through that, right? And so there is some interaction, and that's how this process happens, through some interaction of the electron orbital with the nucleus. And so here it's really like from the continuum, goes down into, for example, the L shell, and then it excites the nucleus. The communication is done via a virtual photon, in that sense, if you do the math, or in the bound states from like the M to the L shell, for example, to the nucleus. And yeah, so basically, like I said, it's strong if energy and wave function overlap, but this is just a resonance argument in that sense. But of course, the inverse process can also happen, right? So again, if we have this nucleus and we have NEAK as an example, the opposite, the time reversal, is called internal conversion in the case of nuclei. So basically, if I have managed to excite my nucleus, it can actually de-excite by throwing an electron out. This is similar to like Auger electrons, for example, where basically the nucleus will take one of its electrons, usually an inner electron, and throws it out with some kinetic energy. And just as I said that the excitation process has a much higher chance of happening, or cross-section, usually a nucleus will decay via emission of an electron. And as you can imagine, if I throw out an electron from the inner shell, I will have X-rays coming in afterwards. So there's lots of background if I manage to excite a nucleus like this. But so this is usually the dominant decay channel of any nucleus, not radiative decay. And this then obviously often has a shorter lifetime, whereas radiative decay has a long lifetime. Yeah, basically that's what I said. So just before I get into the nuclear clock and other things, what are specifically sort of the benefits of actually going to nuclei? Like I said, okay, higher Q factor, are there more benefits basically? Like I also mentioned before, there's narrow lines even in a solid. So I can have high densities of my atoms basically. There's a large spread of energies and lifetime if I look at all the isotopes which have all their different nuclear structures. So for example, an image here, which shows you on the horizontal axis the half-life of the excited state, and at the vertical axis the energy of that state. And compared to, there's a couple of red dots here, these are well-known clocks, basically. So atoms that are used for clocks, but you probably also know the linear ion trap quantum computer of the calcium ion, etc. These are, in that sense, quantum objects that people have been able to manipulate to a high fidelity, basically. Then you see, like popping out is this thorium-229, which I talked about, which we probe with a laser, extremely low, right? Because the rest of the nuclei are over there. Then there's another weird one, which is uranium-235, basically, but usually we don't like to work with that because obvious reasons. And then there's this whole zoo of other excited states that have been also already coherently manipulated to a certain degree, some of them. And we could use all of those. And there's even nuclear excited states that we have not seen decay. So they are all the way up there. And that would be interesting, for example, as a nuclear storage, energy storage medium. So I can store energy in a nucleus, like a couple of kilovolts. And if I can make a very energy dense material, I can put energy in and out, one could produce something like a nuclear battery, for example. Like I said, we see long lifetimes, but obviously you know that lifetime, like T1, T2 time, is not always the same as coherence time. So a very long coherence time is something that still needs to be demonstrated, but at least we have long lifetimes, and the rest is basically still up for experimental research. These things should theoretically be possible. And of